Hi, I'm Ed Calloway. I'm an entertainment architect at AMD, and I build computer and TV products that use a lot of graphics to make a lot of pixels. And I also do a lot of stuff with sound. And I find one of the things that does get forgotten in the rush to AR is everybody thinks about pixels, but not everybody remembers that immersive sound is part of it. So I will work some sound into it. And just following on from what a lot of other people have said, I use the term VR a lot because I grew up with it 2 years ago. But when I do that, I mean not VR alone, but AR, but also other immersive technologies such as video walls, dome projectors, and anything that's visually immersive, and for our sake, uses a lot of pixels. So this is the too long, didn't read, the whole presentation's really up here. I'll be covering basically, what we do and giving a shout out to what I think you people do, and where's it done. But I think this is an interesting tweet from a developer, Nat Brown, in 2015, when he said that VR is about a decade of job security for everybody, as VR requires really more compute, more pixels, more network bandwidth, more 3D modeling. And I think he was right, but his 10 years is up in 2025, and that's not far away. So I'm going to walk a little bit on the pixel side of things on really by 2025, how many pixels are you going to need and how many are you going to be paying for? So this is the obligatory slide that was everywhere in 2016 on what are people going to do with VR. And the really, really good news is this is happening. And listening to the talks today and the dinner on Wednesday night, people are doing real estate, they're doing safety training. I've been involved in a lot of entertainment. People are doing design for space stations. So the good news is, although the sales of VR headsets are not where everybody wanted them to be 3 years ago, the applications are being developed and are being used. So to me, this old slide is actually one of the most important because it is happening now, and you people are doing it. For the people here who don't know what we do, but like you who do know what we do, what AMD does is we make computing power. And really what does that mean? We make silicon, that's silicon CPUs, and those are the parts of a computer that does the add, subtract, multiply, if then else, and moves the data around. But we also do the other side of it, which is these parts on the right, which are the GPUs, or the graphics processing units. And those are really the things that, up until very recently, just made pixels. They drew games, they did game engines, but now what's happening more and more is they're getting used for a lot of mathematical computing and machine learning, where you want a lot, you can have an operation that can be very heavily parallelized and spread out over a lot of computing nodes. So you're going to see a lot more graphics processing units in traditional compute applications in the near future. And where do these things go? Well, really, these CPUs and GPUs come in all kinds of sizes, from a few watts to hundreds of watts, and they go into consumer devices you're familiar with, like PCs, laptops, Apple products. We drive the PlayStation and Xbox game consoles. So there's a lot of consumer products, but they also go into big data centers and cloud computing, because for all the AI applications, there is a lot of data to get through, and you need, these days again, a lot of parallel computing to do that effectively. So historically, where is computing done? Because it affects how much computing you can do, how much power it takes, and how physically big it is. In the past, around the 60s and 70s, all the computing was really on mainframes, and you got a terminal with green text. that was it. If you were in a research lab, maybe you got some graphics, but they were, again, usually green and very slow. Around 1980, the personal computers exploded, PCs, Apples, the early Macs, and that moved a lot of computing onto your desktop, and the mainframe sort of stayed with insurance companies and things. Around 2000, the net exploded, and a lot of computing and certainly providing data storage went back to servers to give you all that web content. 2005 was cell phones, and again, a lot of stuff came back to computing and a phone in your hand, but the data that you were using on that phone came from those servers and even more. So I think the thing is here, there's computing moves around a lot, and it affects how it can be done and why it's done. So what I'm going to talk a bit about farther on is content production, which is things like movies and games. And movie and game content has also moved around between local compute devices like game consoles and remote compute devices like a big server room rendering a movie. In the past, most of a game would be rendered in a game studio, or all of a film would be rendered in a film studio. And for a film, you just play it. For a game, yeah, you've got some interaction, but you're really moving around in a fairly scripted way in a world that the content developer built back in the studio. What's happening now more and more is the content may start over here in some studio or server, but it's finished on your local device. And by finished, I think the best example is with augmented reality. You're adding content that somebody built somewhere else, and you're mixing that in with your real world video that you've provided. So you're mixing local and remote content in real time, and that trend is growing. Though there's with really high-speed data pipes and 5G networks, you're not going to really know or care where your computing is done, where your content was finished. It's all going to look real in front of you. So I like pixels, and this is a little bit of history on how many pixels. And this goes back to the early days of TV around early 1930s. TVs were mechanical. There was a big spinning disc with holes in it, and that was your scanning system. And you got about a 30 by 30 pixel image, which, to put it into context, is far less pixels than you get with your little arrow cursor in Windows. By 1941, they pretty much settled on the standard for television, and really up through to VGA, the number of pixels changed very little. What's happened since 1987, though, is we're getting more and more pixels through HD, 4K. 4K is in the stores now. You can go to Best Buy and buy a nice 4K television. 8K displays are now being shown at trade shows, and 16K displays are very close, and I'm sure I'll see one at CES. But the interesting thing is, if you plot that rise of pixels against time, the slope is getting very, very high. And if you follow that through, we're going to be at around 1 billion pixels around 2025, when that other guy predicted we'd be out of a job. So there's a lot more pixels coming. I think, but the other thing is, as well as more pixels, we're getting better pixels. Things that have changed with high dynamic range, UHD, there's more data in the pixels. Pixels used to be black and white. That was 1 bit per pixel. For most of this time here, pixels were 24 bits per pixel. We're now heading to 48 and more bits per pixel and floating point pixels. so that we can create more reality with very dark scenes, very light scenes. So the amount of data in a pixel is going up. And the other thing that's happening is the number of frames per second being delivered is going up from 24 frames per second per film. For gaming and VR, we're up at 90 to over 200 frames a second. So if you multiply out the increasing number of pixels, the increasing amount of data in pixels, and the faster frame rates, there's huge computing growth happening now and required in the future to give us the pixels that, according to this completely unemotional graph, we seem to be asking for almost the last 100 years. So why do we need more pixels? It's because nobody ever really wants to see pixels. People want pictures. And pixels, which are those little square things, are very distracting. So this is that's a screenshot from inside a typical head-mount display. And I'm not sure if you can see it from where you're sitting, but there's this funny pattern all over it. And that's called screen door effect. And that's because the pixels in a VR headset are so big in a current headset, because they're around 2.5K pixels, that you can see them. And so what I find is if the content is amazing, my brain goes, I see the content, and I don't see the pixels. But as soon as the content drops below stunning, my brain goes, I see a lot of pixels and they're kind of moving. So VR headsets have a long way to go to get to truly believable immersion. And that's one of the things driving the need for more pixels, is we just never want to see them. Going almost to science, not quite. How many pixels do you need? The answer is, it really depends, and it doesn't, what really matters is, when you get to the retina of your eye, can you resolve two objects? Do they appear as two separate things on the retina, or do they blend? And a very rough measure of that is if the angle between those two objects in the real world is around 0.02 degrees, there's some agreement that at that point the pixels are roughly invisible. There's a lot of discussion around that number, and it can be a lot bigger or a lot smaller, depending on your eyes and a lot of viewing conditions. But that's roughly how it works. And one of the key things to take away from here is a lot of pixels close look the same, smaller pixels close look the same as bigger pixels far away. So when you're trying to figure out if you have enough pixels, it's not just how many you have, but what's your field of view, what's the angle, and how far away are they? So don't just count pixels, think about where they are and what's your field of view. So if we take that back to this slide, where are we today, and where do we really need to go with numbers of pixels? And if we stick with that idea that around this area they're kind of invisible, well, on a desktop monitor today where it's this far away and this big, and you're only seeing an angle of about 60 degrees, roughly, 4,000 pixels crammed into that little amount of space, they're pretty much invisible. If you can sit at a desktop monitor distance and see pixels on a 4K monitor, you have fabulous eyes. But if you take a VR headset, you've got about 2,500 pixels horizontally, but they're spread over this much distance. So you've taken a few pixels and they're stretched. So VR headsets and AR headsets have a long way to go. But again, there's differences. For a lot of reasons, AR headsets tend to have a narrow field of view. So you're going to be able to get by with 4K pixels in that narrow field of view and not see them. But when you get into, as you stay with VR, and you're trying to do those very wide field of views, you're going to need those 8,000 to 16,000 pixels to guarantee they're invisible. And if you're paying for those VR headsets, you're also going to need good optics, because a lot of the optics in VR headsets today are really, they're prizes at the bottom of a Cheerios box. They're not very good, and there's a lot of lens distortion that makes the pixels look even worse. So jumping into some of the uses of pixels, one of the things we're interested in a lot is movie production. And there's, again, a lot of stuff on this slide, but in the middle, there's production. There's people making a movie, they've got cameras, they're moving around, they're on a set. For, again, 100 years, that's where most of the action was, in the filming. Your pre-production on the left, you were writing a script, you were designing costumes, you were painting sets, a small amount of work. And your post-production was, you'd do some physical cutting of the film, you'd add a few very simple optical effects, and you'd add sound. What's happened now is that all of these processes have gone very, very digital. The pre-visualization, that's actually not showing up, but that's actually a car. Pre-visualization is now done a lot of times with game engines. So they'll render a whole scene of a movie. What was 10 years ago in a very crude fashion, they'll render it sometimes in full movie quality. And they'll use that to give the director more ideas. They'll use it to sell the project around Hollywood. But and they'll also now, as those assets that they create in pre-visualization get better and better quality, they'll start bringing those assets directly into the film. And they don't have to recreate them from, say, a very crude image to the real one. Post-production actually got started almost a little earlier, around 1990. There were some digital effects. Now you get many, many movies where the digital post-production effects are bigger and more expensive than the filming. So all of these three stages have are now about equal in size and equal in cost in a lot of movies, and it's all because of digital production and trying to create an immersive world. So how did that look in 2007? Actually fairly sophisticated. Here's James Cameron on the set of Avatar, and he's actually got a virtual camera, which is a very, it's a fancy monitor. There's the actors. They're all in motion capture suits. And this is what he's seeing on that virtual camera in real time. So he's seeing, and I hope, oh, sorry, I have to do that. So while those actors are moving around in real time, their motions are getting mapped onto some, for the time sophisticated, but for now fairly crude representations of the actors, crude representations of the background. But that allows the director to get a pretty good idea on how the film is going to look, even though that's what's happening. He can see this, and that's really the heart of virtual production. At this point, I'm going to skip through a lot of stuff. Okay, so part of virtual production is green screen. This is me. I was in front of a green screen, and then they took us. The green screen got replaced by a beautiful video of a waterfall that was actually running in post-production.
Is that our mug?
That is an immersed mug. So that's just to prove it was real. The mug is real. And green screen's been used for many, many years in Hollywood. But the problem with green screen is if I move around, I'm just moving in front of a video that doesn't know I'm there. If the camera moves, what should happen if the camera moves from here to here, the position of that waterfall relative to my head should move, but it doesn't if you're just putting things in a green screen. And to create that in post-production is very expensive. So what you're seeing here is something we showed in SIGGRAPH together with a partner. This is using virtual reality and virtual production in real time to create a virtual set extension. So what you're looking at is he's got a camera, and up there is a Vive lighthouse, and on the camera, what you can't see, is a Vive tracker. So what's happening in real time is there's a giant rear projection screen. The cameraman will be moving around, and as the camera moves, that information of where it is and what it's looking at is passed back to a game engine that is in real time rendering this room. And there's really interesting things going on here because the camera is picking up the room lighting and the lighting on the person, and there's other cameras that can also pick up room lighting. That's getting fed into the game engine so that the lighting on the objects in the game engine matches the room. And the game engine is projecting on this screen, and that's backlighting the other things on the set. So it's a real virtual set extension. This is a short video of that in action. It's very, very different from a green screen.
Hi, I'm Frank Pitts with the Immersive Technology team at A&D. We're really excited to be working on some very cool projects in collaboration with Epic, Unreal 4 Engine, and in this case, AR Wall out of Hollywood. This is amazing new technology that adds another tool to the toolkit for virtual production. We've got a system here put together by A&D featuring the Threadripper and multiple WX9100 video cards. This gives us the power to do what you're seeing here behind me, which is the ability to have a camera looking at a scene in the real world and have a virtual set extension that extends into the wall. This is akin to what you would do with a green screen, but now there's no green screen. The camera is free to move around. You see your process happening right there in the camera. So what's in the virtual world likes the real world, and you don't have green spill, you don't have problems with hair. It's an amazing system, and it's kind of the holy grail of virtual production to be able to make a seamless composite on the fly.
So that's what's happening right now in film production, but you can, instead of adding all that background, very difficultly trying to match camera angle and lighting later in post-production VFX, you can generate that whole room with all its lighting in real time and film it. And when that filming is done, it pretty much looks like that room was there. And it doesn't look like a flat screen anymore. So I'm running low on time, so we're going to skip so many things. There's just a quick view of, I promised some stuff on going faster. So everybody who's got a Mac Pro goes to Starbucks, does all their thinking in Starbucks. But if what they're doing is creating high-speed or high-quality movie content, if you try to render movie content on a thin and light battery-powered laptop, you're going to wait a very, very long time. And that's really got nothing to do with whether it's a Mac or whose chips are inside. It's just the power envelope. If you're down at a few watts of power, you cannot do a lot of movie quality compute. To give you a rough idea, to render a frame in a movie can take 9 hours on a farm. When you're doing VR real time, you're rendering 90 frames a second. There's this giant world. So what you can do is you can add an external box over Thunderbolt to a lot of laptops, such as the Mac Pro, throw in one of our Radeons, and then this is a review from 9to5mac.com, and they were just showing DaVinci Resolve, which probably a lot of you here have used. If you have a thing with a lot of special effects, almost 4 hours on a laptop, 14 to 20 minutes with an external graphics card added on. And to me, that's really cool because it says you can still use that thin and light kind of laptop to go to a nice place, do some thinking, do some preliminary work, but you don't have to buy another computer to get your fast work done. You can do it at your desk with an add-on box. This is the latest news from Wednesday of this week. We announced some data center parts, and so where the other thing was a laptop, this is the latest for the data center. And what we have here is GPUs that have very, very fast interconnects. There's 100 gigabytes per second link that can go between, gigabytes per second link that can go between the cards. There's PCIe 4X 4.0 links at 64 gigabytes per second back to the central processor. There's, the interesting thing is, there's floating point 64 data if you want to do really high precision work at a good speed. But if you're doing machine learning and you're doing inference, you really only need 4 bits of data, so you can go a lot faster. And really the reason this is here is just to show there is that wide range between things you do on a server on very big iron, right down to things you do in a laptop. It's all about compute. It's all, for me, it's all about pixels. For other people, it's all about machine learning. So, because people are starting to move and it's time. So what do you do? Basically, don't forget that these days your compute can be anywhere. It can be in the cloud. It can be in your phone. It can be in your laptop. More pixels are coming. We need to go to 8 or 16K for VR, and 16K is right around the corner. We can drive it now. The monitors are coming. And definitely go parallel. If you've got any of your software people still writing single-threaded code, it doesn't. Just keep in mind that single-threaded code will never go faster, no matter how cleverly they write it, because clock speeds are going up very, very slowly. If you want to double the speed of a computer just by clock speed, I don't know, wait 5 years, wait 10 years. But if you get that same software person to write a multi-threaded app, you can pick up a 32-core CPU today and run 32 times faster. I'll be long dead before clocks are 32 times faster, so don't forget to get people to write multi-threaded. That's it.